Our presentation for IJCAR 2020 is on the web application we have developed called Sequoia. Sequoia is a tool that lets you build sequent calculus proofs. It presents a friendly and intuitive interface for creating your own calculus systems, building proof trees with the rules in these calculus systems, and automatically testing the simple cases of important properties for these calculus systems. In our presentation, we will go over the three core modules of Sequoia: the custom calculus system creation, the proof tree construction, and the meta property proof checking. Let's get started. When logged into Sequoia, we are greeted to the home page, which includes all our calculus systems and the interface for creating new ones. We have the ability to make our own custom calculus by giving it a title and a description, or we can work with any of the predefined calculus systems below. For the purposes of our demo, we will work with a predefined calculus, but we will change it a bit to transform it to our own custom calculus and demonstrate the different aspects of calculus creation and modification. Let's use system LJ. On this calculus systems rules page, we have its title and description, which we can edit. And of course, we have all the rules specified for this calculus. The rules have a variety of different symbols, and these symbols are actually defined in the rules symbols table below. For our Sequoia system, we enforce the fact that all rules must only contain symbols defined in this rules symbols table. Right now we have a number of different symbols predefined, but we can add new ones, modify old ones, and delete any we don't want or need. The symbols that we can use are any that can be understood in LaTeX, and the way we define them is through their type. The different types we have available are atom variables, formula variables, context variables, connectives, sequence signs, and context separators. Now let's go over how to add a new rule to the system. Let's add a rule and left, which combines the aspects of and left 1 and and left 2, but we get to keep both subformulas A and B in our premise. So let's do that now. So now we're on the rule creation page. We can give our rule its name, but we must also specify its type. The different types of rules we can have are logical, axiom, structural, and cut, where cut is a special kind of structural rule. In our case, we want logical. We must also give a side and main connective if applicable. In our case, the side will be left, and the main connective will be the conjunction, which we write as wedge for LaTeX. Again, our premise should include both A and B, as we said, and the conclusion will be the same, where it will be gamma A conjunction B entails C. We can preview our rule to see the LaTeX rendering of it, and when we're satisfied, we can add the rule. And here we are, we get the and left rule that we created. We can also modify any of the existing rules. So let's go to or left, let's edit that. Let's make it so that the context doesn't split into the different premises. So name it all the same context, gamma. And when we preview it, this is the kind of rule we want. We can update it. And here we have our updated or left rule. We can also delete any existing rules by simply deleting them like this. And this will just remove them from the calculus very easily. Deleting symbols is a bit more complicated. When we go to delete a symbol, we get a warning. And this warning basically is telling us that some of the symbols might be integral parts to the definitions of rules. And so deleting those symbols will also delete any rules relying on those symbols for their definition. And this is because, again, we enforce the fact that all rules must only contain symbols that are already defined in the symbols table. So we don't want to do that, so we'll just say no. But now that we have specified our calculus to our liking slightly, we can begin building our proof trees and show the proof tree module. On the proof tree construction page, we have our rules sidebar with all the rules we defined earlier, the usable symbols table, which just shows all the symbols we can use in a valid sequence, and the initial sequence that we want to build our tree off of. This is where the user inserts that usable sequence. So if we insert one and we preview, we get the LaTeX rendering of that sequence. But before we can start building our tree, we need to make sure that all the term symbols like theta, f, g, and h, all these term symbols are defined earlier. And we define them in the sequence terms symbols table. So right now we've already defined these terms to save time. So let's start building our tree. The actual core work done in rule application in the backend is through unification, specifically unification between the rule conclusion and the sequence that the rule is being applied on. The system description paper goes into more detail on how this is used for rule application. So let's take our sequence and apply a very simple rule. We'll apply or write to. We know that the rule should only apply in one way, and the resulting tree shows one rule application. But what about a rule that could apply in different ways? So if we apply the or left rule, what we get is a prompt that tells us that we have two sets of premises that can result from that rule application, reflected by applying the rule on this disjunction formula or this one. Let's suppose we apply it to this one. We choose this set of premises, and then this is our resulting tree. What about a rule that can apply in multiple ways by splitting the context? So if we do and write on that sequence, we get a prompt that shows us all the different ways the rule can apply due to splitting. Now if we choose this one, the rule applies, but we also see something on the left, and this is where our constraint list resides. And here is a constraint in our constraint list. Now, the constraints are also detailed in the paper, but essentially for the user, the constraint list as a whole is a way to see how the context variables change due to different rule applications throughout the tree, which is important when working with schematic trees. If I apply another splitting rule on this sequence maybe, implication left splits, well, I get another prompt telling me what to choose if I just choose a random one. Well, the constraint list has been modified to better reflect the changes made to the tree. And note that the original context here is copied to both these premises from that rule or left that we had. But the two different rules that can split and write and implication left, they don't necessarily have to split in the same manner. So we have two different sets of context variables, which is reflected in the constraint list. Of course, we can undo any rules that we don't want to apply. And when we're satisfied with our tree and we want to just see the LaTeX, we just click see LaTeX and we get the LaTeX encoding of the tree as well as the constraints. And we can, of course, send it as an email in the text body. So now that we've gone over the tree building module, my colleague Hashim will present the automated properties testing module for the end.
This is the page where you go to check meta properties of your defined calculus, such as identity expansion, weakening admissibility, and permutability. The permutability page allows you to select two rules such as and right and or left. Then Sequoia can check if the first rule permutes above the second rule, and in this case it does. Sequoia also shows you the possible cases where or left is applied above and right, and how they can be transformed into cases where and right is applied above or left. Each case is in a separate box, and if no transformation is shown, that means the case has failed. To check this property, Sequoia generates a set T1 with all derivation trees where or left is applied above and right, and another set T2 with all derivation trees where and right is applied above or left. Then for each tree T in T1, we try to find another tree T prime in T2 that T can be transformed into. To decide if a proof tree T can be transformed into another proof tree T prime, we assume that T is closed, meaning each open premise in T has a proof. In this case, we have the proofs D, E, and F. Then, we use those proofs alongside the axioms from the calculus to try to close the open premises in T prime. We say that a proof D can be used to close an open premise in T prime if the sequent it's trying to prove has the same formulas and the context variables are compatible with the set of constraints that we already have. To check identity expansion, Sequoia tries to automate the usual proof with one case per connective. Clicking on the box with the connective on it shows the user the proof transformation, which transforms an application of the identity rule on the complex formula with the connective into another derivation tree where the identity rule is only applied on subformulas of the main formula. For weakening admissibility, Sequoia checks each context separately. For a specific context, Sequoia tries to automate the usual proof with one case per connective. Clicking the box for that context will show the user the list of cases and whether or not they passed. In general, the property checks done by Sequoia are sound but not complete, and the tricky cases that Sequoia can't do are left to the user to do by hand. This marks the end of our presentation. Thank you for watching, and do you have any questions?